So, I have been working on some stuff related to RL and robotics in the robot learning lab. So I'm at Freiburg. I guess most of you know that, but yeah. So, to start with, what is reinforcement learning? I'll just give a very brief introduction. Like, it's a way to formulate problems as an agent that acts in an environment by sending some actions to it, and it gets a reward and the next state. For example, like say a robot just moves to the left and it just sees what is in the left of the current position. That's the next state. And the reward is something that's defined by us humans, to make the robot do some task. So let's say you want the robot to push a block. You just say, if the block move towards the goal, it gets a positive reward or something like that. So this has been a methodology that I think was in the 90s. It came together from different fields like control theory and behavioral psychology of Skinner, and all these ideas just merged together in 90s, and it became this field called reinforcement learning. And yeah, currently we have this neural networks that has been used for RL. It's called deep reinforcement learning, and I guess many of you might have seen this. Like AlphaGo is one of the recent achievements in the game of Go, which is a big so I think it's a Chinese game where you have the checkers and you have to place one white and black checker. Each person goes. It's a two-player game, and it's a very tough game. People thought it wouldn't be solved in maybe 20 years or something, and I mean in the next 2 decades, and it got solved using reinforcement learning for with the help of deep learning. Like, you have both neural networks, and you use the neural networks in the context of something called Monte Carlo search, which is it's a way of doing reinforcement learning in a way. And then I mean the rightmost thing is the recent Nature article on reinforcement learning being used in fusion reactors to control something. I haven't read it yet. I just put it up. But you could probably see what it is. Like, to control the plasma. I mean, it's a control problem, and they just DeepMind in collaboration with Fusion Lab just used RL for this. Like, so you can see that it can be used in very pretty diverse settings, from games to fusion reactors, and in between for what we care about. It's in robotics. Like, this animal is a, I think, commercially available robot dog, where they use reinforcement learning for control. Like, control is like just the low level control of its motors that control the legs. So instead of going for the Boston Dynamics approach of trying to model everything, they have just used reinforcement learning in simulation, and then learning policies to robustly control the legs to move in different terrains. So I guess you can see that. I think this animal is open source and available for even, I'm not sure how much. It's not as costly as the Boston Dynamics, I guess. Yeah, then why do we care about reinforcement learning or something like that in robotics? I mean, we know that the pretty much the robots that is used in industry is pretty in a very controlled environment. It's not the human world. It's like we build the environment around the robot, and then the old methods don't really require learning. you just program the robots to do a specific task, and there's not, because there's even though you do those tasks in our world, if we try to do what the industrial robot is doing in in your parking garage or something, it's going to face a lot of variations. Like, I guess one of the thoughts behind using learning methods for robotics is that we want them to work in our environment, but maybe Mars is not really a human environment. So we could get away with most of the traditional robotic stuff, but I guess even in curiosity, I guess they say when the connection goes off, you need some autonomy. Like when the Mars rover is not communicating with us, we need some autonomy or something for that, so that it doesn't fall down a ditch and it learns to navigate it in a robust manner. So I guess you could find some places for autonomy in the Mars rover context. Yeah, and that brings to what I am doing. Like, I'm now currently trying to work on something called multiple generalization across embodiments. Like when you learn some reinforcement learning policies for a robot, it's generally learned for a specific embodiment. Embodiment is just what the robot's physical structure is and what it is capable of in doing in the real world, and what its sensors are. So you already have two different embodiments in the Perseverance, I guess, the rover and the drone. And maybe in the future you have these leg robots or spider robots crawling about the Mars surface. And so the idea is, like, let's say you could do something with RL, like maybe there's different things, like you want to go from one point to another point, you want to plan a path to it, and there's a lot of variations in the environment in which your traditional methods may fail and you want to use RL, and then you can probably this will kick in. But more than the Mars context, I guess it's more applicable towards tasks in which you apply RL in our world. Like, even different forms of robot arms can be thought of as embodiments. Like, you want to train a robot arm to do something, you don't want to again retrain another robot arm which is bit different to do the same thing. So you want essentially something to be shared across different robots. So yeah, that's the main idea behind this. So and in case of even human embodiment is a form of embodiment which can be used to teach a robot. Like, let's say I'll just demonstrate a work where they used inverse reinforcement learning, where you try to learn some rewards from what humans are doing. Like, if a human demonstrates how to lift a ball or something, then you can probably learn a reward function that maps how much a robot is doing that task, and you can use that to train policies for the controller. And people have really done that recently. I'll just show on the next slides or something. Yeah, and there are different ways to categorize reinforcement learning. There's model-based reinforcement learning and model-free reinforcement learning. You can think of it broadly as model being like, if I do this action, what would be the next state? If you try to explicitly model it, then it's called model-based reinforcement learning. And model-free is, you just observe something in the world, the state, and then you try to act on it directly. You don't explicitly try to model it in your learning process. Like, you don't have a specific model where you can give an action and then try to generate what the next state would be. So it has both pros and cons. And model based is important for robotics because it allows you to do stuff with less samples. You don't need millions of samples, because the model is learning from a very dense signal. So every state you get the next state, and it's kind of like supervised learning where you have a good signal to learn something. But if you for model free reinforcement learning, the only signal is the reward, which is very sparse signal, where you will get it probably only at the end of the task when you finish the task or something. So that's why model based reinforcement learning is a bit more popular for robotics, and it's been I mean people are trying to use it in different contexts. And I didn't put it up here. Inverse reinforcement learning is something that is really getting looked at a lot, because we have so much demonstration in YouTube of humans doing different things. Probably can somehow exploit it and use it for then you don't have to define a reward, because all these reinforcement learning problems have the problem where a human has to give a specific reward function for each state, which is a very which might be easy for say pushing a block, but might not be really trivial to design a reward function for something more complicated. Like you want to do a hierarchical task of placing something on over uh, I mean, a bunch of tasks composed together might be very hard to define a reward signal where these robots don't exploit it and just find a loophole and don't do the real task. So inverse reinforcement learning, I just started seeing a lot of papers that come out. Maybe that would be the way where it is really useful in robotics, at least in the short term. And that comes to world models. So in model, it's a model based approach where you use neural networks to essentially build a model of the world. And the model of the world is like you take in pixels and you try to predict what the next set of pixels would be. I mean, it's like a video prediction task where you take the video that has been happening till now and then predict the next frame. So essentially the video's observation, which is like a state, but not really, because you can't. State has a bit more formal notation regarding to Markov decision process. Like everything could be like you can just given a state, you can just predict what to do next. You don't need the history of everything. But observations are a bit more tricky. Like you don't have the exact information about what the state is. I mean, maybe that is too formal, but yeah. So here you just try to learn a model of the observations. Like given observation, you try to extract the state out of it. And you could think of this problem as, let's say you had a neural net that can simulate the environment. So that's essentially what this is doing. Like you are building a neural net that can simulate what the environment is. Then you can do multiple things with it. You can do something called planning, where it could be like a offline planning where you can just say, I mean, I'm at this state. Let's just plan ahead. Let me just say, I give this action to the neural net instead of the real environment and see what happens next. And you can plan. You can simulate trajectories like this, and then you can find the optimal set of actions that can lead to the best rewards. This could be done at each time step in the real world, but it's very costly. So the first thing where this world model approach really worked was this paper by Schmiduber and Ha, where they used it on I think this is the Doom shooting environment where they use the variational autoencoder. So what web autoencoder is it tries to learn a representation of the real world so that you can act upon this representation instead of the pixels. So the world model can essentially take in the image and create a representation of it and then work on it. So then there is a small controller, the C, where it takes the representation from the VAE, which is the Z, and the H from the RNN, which is like which is modeling both the time and the current state. So the Z is a representation of the world at the current step, and H is the history of the states which the RNN has extracted. And yeah, the controller tries to take it and predict whether you have to shoot or move left or right in this environment. I mean, here they use both model-based and model-free approaches. I'll explain it better in this context of this dreamer thing. So the dreamer is the planet. Okay, sorry. The planet is this thing on the right where you are learning a model where you take in an image and try to encode it and compute a state, and you have essentially a way to predict the next state without the image, the future images. You just have the current image, and then you can just work in the latent representations. You don't need an image at all. Like this RNN will take in this this encoder will take in this image, and then the RNN, you can just extrapolate what will happen in the next state, but in the latent space. The latent space is like a representation that we learn through the process. Like we do this encoding decoding process to learn a latent representation, and then which is a very low dimensional thing. You don't need all the pixels. So the idea is like when you want to work on a pixel space and predict the pixels, you will probably not predict them very well, and you don't really want to work on the pixels. You just want some states from the real world, like maybe where the robot is, what its arm is doing, some few factors. But the problem is we just want to learn to do that by representation learning. That is, you want to learn what is a good representation for given an image, and then you can just use that to plan ahead. That is what this Planet paper, which Google 2019 released, where you learn policy. You just learn this world model, then you can extrapolate many trajectories, and you during inference you just have this world model, and you say I am at this state. I'll just dream ahead for few steps and find which is the optimal set of actions that get the best reward. You do it in each step during inference, which is really costly, but this works. This worked at the time for bit complex tasks like controlling the spider in this simulated environment, which is a continuous control task where you have to give this signal. Actions are basically like continuous number from a floating point number, which you have to give it to the controller, and then it tries to move execute the action, and you want to essentially the spider to move. So this world model approach worked, and the main idea is here it solved the task in very less number of samples. So you can just think like model based RL will help in sample efficiency, which is really important for robotics. Then came this dreamer, where they essentially did what the world models paper did, where you have a controller, and then you can use this world model, and then instead of just planning ahead for a few steps, you can then use the controller's dreaming capabilities and just train another agent on it. So you imagine ahead for a few steps. So instead of your agent training in the real world, it's just training in your simulated neural network. Your simulated neural network now acts as an environment, and what advantage it gives us, you can now train in a very low dimensional space of this latent space. Your neural network doesn't need to see the entire image as an input. It just needs to see the small latent space of the RNN, and then it can just train ahead using the dream of the RNN. So dream is just the extrapolated latent spaces.
I may have missed it when you explained it earlier, but how does the world model approach avoid having to explicitly model the reward function, because you're still predicting and getting rewards? So what are you doing instead of an explicit reward function?
Yeah, there is still a reward function in these approaches. Like you assume that you have a reward, and the world model will predict the next state and the reward. So while doing planning, your world model can take an action and give you the next state and the reward. So you you try to find the optimal set of actions that give you the best
Okay, so
sum
you
of
do have
rewards.
to define
Yeah,
the entire world space. Okay, I
yeah.
understand.
In the approaches in the world model one, and here it's a gaming environment where you already have some points which you can use as a reward, and for some continuous control tasks you do have a explicit reward function here. So the only thing I guess this models avoid help out in robotics context is it removes the sample, it gives you sample efficiency. So this model based reinforcement learning stuff work really well for given a limited number of samples. When you have too much, when you can train on a very good simulation or something, maybe model free approaches would be good. But let's say you want to do this in the real world, then model based approaches really shine there. So what Dreamer did was just basically use a model based approach, then train another neural network on this. So one really cool thing about this is, so you can see this black arrows in this GIF where you see something propagating back. I mean, 1 second. So you can see that this is like a dreaming thing. So your actions are given by a neural network, which gives to the world model, and it gives you the reward and the action, and it keeps going. So you can just simulate ahead for some time, and now you can just sum up the rewards from the world model and back propagate through the world model. By back, I mean like you can calculate the gradients through the world model. Maybe this, sorry, I think, yeah. So by that I mean that in the real world you cannot like query the real world by saying what if I had done. You can't do a gradient descent on the real world directly. Like you can't say if I had done this action a bit differently, what would have been the outcome. But since you're simulating the world as a neural network, you can now adjust your parameters in a way directly. You have a very rich signal where you can say, had I, because your world is now a neural network, you can now adjust your parameters in a way that it can increase the reward without having to do too much trial and error. Like you can think of this as, I mean, the world model acts as a back propagatable gradient descentable graph through which you can put action through, and it spits out the reward, and from the reward you can calculate the gradients, the how much I change my parameters in a way that the world model is satisfied and giving a bigger reward. So this is a really cool idea which allowed these people to combine model based and model free RL in a very tight manner. So you have a very rich signal that can go through the world model, and you can get these you can train an agent very fast basically. Yeah, then I mean this is just a research environment in which I am working on. So this has been introduced for the inverse RL setting, where I just want to give a contrast on how this cross embodiment setting works in inverse RL. So here these bots are two embodiments you can think of, and they have to move these blocks to the end. And you have videos of people demonstrating it in the top left. So a human basically says, just demonstrates the task. Sorry. So you have different videos of recordings of these demonstrations, and here interesting part is they learn to, okay, what is common across these worlds. Like you can think of a notion of task completion as being the common thing across different embodiments. Like a human can see different, whether it's a legged robot or a wheeled robot, and see whether it has moved towards a goal. Like maybe if the goal is like place at top of a building, whether a legged robot took a staircase or a wheeled robot rolled over the ramps, you don't care about it. Human can see that it's halfway through. So there's this notion of consistency across different embodiments in terms of this temporal consistency. Like you have this video of different embodiments, and we can have a rough guess on what these robots are doing, like at what point of the task the robot has completed. So here, this is just a proof of concept where they have used it on this very simple environment, and they have trained temporal consistency representations. What they do is they take different videos and say that they just give it to a neural net and say that the representation should be consistent across time, like across different videos. So even if the videos aren't aligned really, I mean, there is some notion of consistency, so you can just train it on a lot of videos and arrive at representations which give you a notion of task completion. Then you can use this as a reward and then train a reinforcement learning on it. So you can give the goal states and get a representation for it. The goal state is probably the end of the 3 blocks being moved to the pink row, and then say then your reinforcement learning model gets in the current image. Then you can say, you can compute a distance measure between this and the last the goal state, and that becomes your reward. So this is a really cool approach that I guess which we will see more for this inverse RL setting, where you have videos of demonstrations, and you can directly map it to a reward function and train a RL model on it. Yeah, and this was another thing I just saw recently. So in this work, they have learned this entirely from YouTube videos, where you don't have really alignments between, like you have different videos of people doing something with their hands, and they have essentially figured out a method where they can take in the hand videos and then do some self-supervised learning on it in a, I mean, like I just saw this yesterday, so I haven't really gone too much into it, but they use the you don't have any robot to human mapping there, but they found a unsupervised way to map it, then learn representations, and then train a model to do things like this. Like you can just demonstrate something to it and it can do it. And here the thing is, it can work on different backgrounds, different hands, and they don't really because they trained it on a lot of YouTube videos, it generalizes really well. I maybe I can do a better job explaining it, because I don't really understand it right now, but I just found it because this seems to be a really something I'm working on. Like I want to make the robots work robustly, and this seems to be one of the work that did that. Yeah, so that's it. So currently I have been working on this and trying to use not the inverse reinforcement learning setting, but I come up with just the normal reinforcement setting where you can share world models across different embodiments. So because the world has some consistency to it, even though the robots might differ in the way they do things. So how can you exploit that so that, I mean, if you have 100 robots, it's better to get 100 samples from 100 different robots. It's easier, and then train something with it, rather than having to have a single robot go around picking up samples of the world and then training something on it. So the essential, my research currently focuses on that stuff. Like, yeah. So that's it. Sorry. Yeah, now we can discuss.
So does anybody have any questions about using reinforcement learning or about learning between robots?
Have you started any implementation or learning?
Yeah,
Sai?
so I started with the robot arm, and currently, currently it has been I mean, robot arm manipulation using directly pixels is a bit tricky. So we have some proof of concept ideas to work on, like how to share a world model between different RL agents. And so we so instead of doing it on the robot arm, which takes a long to train a single thing, we initially want to have a work that generalizes across this small simple environment. And then, even though it seems like how will this work for the robot arm, like generally people do this, they train some new approach on the small environments, and then if it works, then you can do it on a robot arm. So currently, yeah, I'm just trying to do this world model thing on this X magical environment where you have these cute bots to move the boxes across the line. And yeah, you can think of each of them as a robot, and then yeah.
So the thing about this particular simple example, did you construct this, or is this from this Zaka paper?
Yeah, this is from this paper. It's called, yeah.
So the way you're doing this is you're imposing a metric on the goal space on the world model. So in this case, there's 3 objects that have to move to goal positions. So if 2 of them are in the right positions, you're kind of 2/3 of the way there. So it's kind of a well-behaved space where the goals kind of have that function as a nice smooth one. So most worlds will be more complicated, but giving you that, there's another aspect that's hidden here that I don't know that it'll be easy to separate out, which is, in this case, you can actually separate out the world model and the robot model fairly cleanly. Like both the robots, even though one is a circle and another is like a bar that can push 2 things at once, they're fundamentally like, if you sort of like, one way to see this is if you make the world very big and the robots very small relatively, they can be approximated by points, for example. So the state of the robot will be X, Y, and the state of the goal would be 3 points positioned somewhere, right? But most robots are not that separable from the world they're in, which is why the standard approach in robots is to use a configuration space, right? Where if you have, for example, say one of them was a circular robot, and that's one way to move things, like pushing things around. But say the other one was like a real complex manipulator, as in like a 3-link mechanism anchored at one end. And then you would have, I guess that would be 3 angles plus 2 dimensions in the space. You would have a total 5-dimension configuration space. And my point is, you wouldn't be able to separate that out clearly into robot states versus world states. Does that make sense? Because parts of the world state would not be reachable based on the configuration of the robot. So it's not clear to me that you can actually consistently separate the world in a way that's similar across embodiments, by which let me try to put this simply. You're saying you want to generalize the learning across embodiments of the robot. And I believe the embodiment of the world is coupled to that in a way that won't be easily separable.
Yeah,
so it'll be
wheeled. If you have just a ramp, wheeled robot can move up it. A legged robot can't. There is
good example.
There is there are some states which is not reachable by few embodiments, and the idea I guess would be to learn a better world model. And probably you it's not like you can't learn a brain that is completely separated from the embodiment. You have to have something in the end. You just want that to be minimal. So I mean, you have some, you can think of this as a notion of the humans can see other humans do something and they can replicate it or something like that. But in the end, there has to be some learning which is tied to the body, to the embodiment. Like, so it's.
I think I'm making a slightly different point, which is it's not just the learning that is tied to the body, but the perception of the world itself, like a bacteria sees a very different world than the world I see, even though we are occupying maybe the same room here. The bacteria sees chemical gradients and various other things, and it sees like 10 dimensions of the world I can't see at all, whereas I can see 10 dimensions of the world the bacteria can't see at all. So the world you see is an embodiment of the body you're in. Something like that is what I'm getting at, which means that it would be interesting to see what are the conditions under which you can actually create a sort of cross-embodiment reinforcement world model function. It's to me, it seems like it would be relatively easy to construct like weird counterexamples where two robots see worlds in such completely different ways. You can't actually put them in the same reward space, right? Something like that could be possible. So I'm wondering what the necessary conditions are to actually use this approach.
Yeah, we are also. Yeah, I'm also thinking about that. Like, where does it make sense? And like even in a formal, in both very abstract way and even in a formal MDP way, like to put it as a Markov decision process, what is actually being shared across different embodiments. And yeah, that's a line of research. The practical end goal here is like the lab I'm working at has a grant on legged robots. So they want to have a 6-year project on making legged robots. I mean, research on different aspects of making legged robots work on a tight urban environment or something like that. So they have already done some stuff in the wheeled robot thing. So it will be essentially to see what you can share between a wheeled robot and a legged robot in some ways. It won't be a low-level control thing where you try to control the motors or something. It's more like high-level planning or planning where you might use RL or inverse RL there. So, yeah.
Yeah, I think those two are close enough that you could actually even formalize the closeness, right? Like you could put both in a bounding box and say, define the convex hull of the legged robot or the wheeled robot, and therefore you can approximate it as a solid body in a large space. So certain location and navigation things will be formally the same. But I think it's interesting to know what conditions are and how much you can stress them. Like if you had a really long snake-shaped robot that's as long as a city street, and it's like goes around like a snake, what can it share with a small car-sized wheeled robot? So even there, I believe some things can be shared. So it would be good to know how would you actually compute what can be shared, and how, under what conditions would you say, no, these two robots see the world too differently and nothing can be transported, so let's not try. So it would be interesting to see what the dividing line is.
Yeah, I guess to formalize that into some metric or something would be really cool. Like what can be shared, or how much of, I don't know, how much the world models are consistent across two sensory observations, so that you can actually learn something that is not conflicting, which is general across two things, or useful across two things at least.
Did the authors of this paper try it on any real robots, or was it just simulation?
I guess I can see 1 second. I think they used humans demonstrating it. Maybe I think they have a video.
But this is some open AI gym thing, right?
So yeah, I mean, this is something they defined it. This X magical environment is something they defined it, I guess.
And this is reinforcement learning, right? Not one of the other million neural net approaches.
No, yeah, it's inverse reinforcement learning, where they learn the reward function and then use it to train a robot model. So inverse reinforcement learning is like you want to learn the reward function from some demonstration, and then you can use that as a reward to train your robot. Or I guess here, 1 second, I don't. No, Yeah, they have a real data set as well.
Huh. So is there a significance to the fact that in the lower right video, it looks like the person is wearing a black glove, and in the lower left, it looks like they're wearing a red glove or something? Are they learning like forms that, huh?
I guess it's has to. I guess
Not a
I
glove,
guess it's
okay,
different.
yeah, it's a gripper shaped like the actual robot,
Yeah.
I guess. Okay.
So the learning is basically from these images, not from like the
Yeah.
actual sensor readings.
This is just learning from pixels. Like
Okay.
you try to learn this, and then the robot, I guess the RL model's action space would be the degree of freedoms of the robot arm. So the final thing you learn. So I think one thing cool here is they just use these videos and impose some sort of temporal consistency, which is like a notion of task progress. You know that, I mean, when the pen is in the cup or something, it's you are done, you're halfway through, and it's when your pen is near the cup. So even across different embodiments trying to do the task, you have some consistency. But here, I mean, it's just the tools are different. That's the embodiment.
I have a question about model-based reinforcement learning. And the question is, where do you get the model from?
So you act on the real world. I mean, you can act with some policy, like generally you take in some pixels in, and you initially you have a dumb model, maybe it's initialized randomly or something, and it tries to give action out. And then you can just query the world. You have the environment, and you have to query it by giving it an action and getting the next step from it. So then I mean, for something like a robot arm, you just move a controller, some control signal a little bit, then probably a robot arm will move like this. Then you have the next state is the image. So you can say, given the current image and this control signal, what the next image would be. So that in pixel space, we'll be learning something like that.
And if you use not model-based, if you use regular reinforcement learning, do you end up with a model when you're done?
No, the model here is the okay, I mean, yeah, the confusion is like the neural networks are called model in both the cases, but in this specific context, model is just the transition function. Like in model-based RL, you are learning the transition from one state to the other state. But in just model-free RL, you learn either something called a value function or a policy. In the end, you learn a policy. Policy is like, given this state, what should I do next? That's all you care about. You don't care about what the world will look like in the next state. You just care about what will be my next action, which has been trained in such a way that it maximizes the reward. So you end up with a model which just learns to map from state to behavior. You don't have state to state. You can think of it in that way. Like model-based reinforcement learning is like you learn a model that simulates the environment, basically. So it's a state-to-state thing. Given this state and action, what would be the next state and the reward? Or you probably can sometimes just don't have to model the reward, you just have to model the states and still do some stuff with it, but generally you need the reward.
So what would be the first step I would do? Let's say I wanted to add reinforcement learning to my robot,
Hmm.
what would be a first easy step to do?
Um,
I mean, we
for
saw your robot bouncing around. So let's say I wanted my robot to also do that.
you mean okay, it's an interesting question. Like if you have some task, maybe I'm not sure. Let's say you
No,
had a task.
let me maybe give you, I have a
uh,
robot.
hmm.
The robot has a mechanism for moving, doesn't matter if it's legs or wheels. And I have some sort of input, let's say a camera. And let's say I want to build a demonstration of reinforcement learning on my robot. So
Okay.
what should I do other than
Yeah.
download softwares?
Hmm. Let's say you had a I mean something you can accomplish better with the classical techniques, but let's say you wanted a robot to follow a lane or something like that.
Yeah.
Let's say you had a lane or path that you can just distinguish by just seeing it. And for the real world, I guess you have to, at least for something like your garden or something, currently from what I have seen, you need to train something in a simulation and then have to make it work in the real world. I don't think you can directly train it. Let's say you wanted to follow a path. If you try to train it on your spider bot, even with model based RL or something, it's not going to work. Like it's going to take too many samples and it's going to be very slow on learning. So the only way to get around it is have a simulation that works well and then train. By train, I mean uh, a simulation where you can set up an environment and then you can maybe download this dreamer or some code and then minimize an objective. Then yeah, it sounds really complicated to do it right now.
To rephrase what you're saying, if I have a big garage and I paint a yellow line
Yeah,
on the floor,
yeah,
and I take my robot, which doesn't know anything, and I put in the right reinforcement learning software, you're saying I can't do it.
I'm
Not
not.
it will take me days, is what you're saying.
Yeah, it could take you days, and your robot has to move up and down and do trial and error quite a while. Maybe with the model based approaches you could, I'm not sure about this specific task, because in robot arm tasks what they do is they try all the experiments in the simulation and then they do actually do it in the real world. For robot arms, they try to train the model in the real world itself. They don't like do the sim to real thing. I mean so you can do it, like it's not impossible. Yeah, that would be a good demonstration. Like you can train the bot to follow a line or something which sounds, I don't know, you can do it without reinforcement learning, but yeah.
So you mentioned before that there's other types of learning. So for this task of learning how to follow a yellow line, is it better to use something that's not reinforcement learning? Is it, in your opinion, some type of learning which will work in an hour or two?
Yeah, by other types I meant like you can use a neural network to get a segmentation map of the world out of it. You can use some pre-trained neural network. Then you can just write code to, I mean, when the center of the, you just want the yellow line to be at the center, right? Like you have to write the code to do that. If you like, you can I mean, you can just define it in such a way that the yellow line should be in the center. The yellow line would be extracted by a semantic segmentation neural network, which is just a sensory thing.
Mhm.
This particular example, they have a lot of kits that do this, like just optical sensor that detects whether you're on a white line or not, and just it sounds like a very small program. Sorry, Rhett, I think
Yeah, I was just going to ask, like, when we talk about simulations, like, oh, you've got to do something in a simulation or else it's going to be too slow. It doesn't have to be, or does it have to be a like full 3D environment with a physics engine trying to replicate the real world? Like, if depending on the level of abstraction your model is operating at, if your simulation consisted of like the position of the yellow line as identified by some other tooling on one axis, like there's just not very much. The simulation is really simple. It's like an integer or something, and then
Yeah,
it's obviously really fast and simple to write. Is that something that's done, or is that like when people talk,
Yeah.
or when I don't know, literature talks about simulation, it's always like, oh, you're using a generalized simulation environment?
yeah. Most of these environments come with two types of observations. Like one is something very dense, like what you're saying, like the position of the robot, the XYZ coordinate, or some coordinate axis with respect to some absolute frame, which is just few numbers. Then it's going to be pretty fast. Like you don't have pixels there. Only when you bring pixels into the picture, like you have the problem of having to have a physics engine, and not just a physics engine. I mean, a photorealistic renderer and all that. NVIDIA has recently worked on a big thing called ISAC. I'm not sure how well it is going for them because they haven't really open sourced anything, and every time you have a bug, you just have to post on their forums or something. But NVIDIA ISAC is really trying to bring some consistency to this type of training from pixels. Like they have a full physics engine simulating everything in the GPU and stuff like that.
But you would only do that if you were training something that was taking pixels and turning it into a decision or something, right?
Yeah. If not, I mean, you can just use a simulator. It's not photorealistic, but it has a physics engine, and then you can get away with it. Like for robot arms, like you can take the, I don't know, tactile sensor and the position, and probably that is enough to learn how to pick an object and place it somewhere. You don't have to really see it. For that, initially when I showed that animal thing, which can walk without tumbling or stuff like that, there's no image sensor for it. They just used RL on just the tactile sensors of the legs, and that's it. They to learn how to stand up and walk in different environments.
This might be stupid from like a research perspective, but on a small scale rover perspective, I just kind of wonder if would be an approachable task to say, like, take my rover that's got 2 motors. I want to train it to somehow like not using a camera at all, but just learn to move forward based on, I don't know, an IMU or something. Like, how do you do that without in a simpler environment? I don't know, it seems like pixels are a generally useful sensor, but like it's also expensive from a computation perspective and from a time perspective.
Yeah, for reinforcement learning, it doesn't care whether you use pixels or you use states. Like you can use all these approaches it's a general thing where I think people just use gazebo and simulate stuff on it and put some IMU or some sensor on it. Then you have an environment. You just have to define probably the reward function, and then you're good to go. Like if your task can be defined as this sensor with some objective as this reward function, and then you can do it without having to, simulate in a GPU, very, very photorealistic environment or something like that.
Speaking of simulators, I'm wondering if it's possible to retrospectively simulate on data. In other words, is it possible for my robot to try to walk and collect data, and then I pass that data through a simulator in order to learn what it should have done? Do you know if there's any work on that?
I'm not sure about simulator, but I think offline reinforcement learning setting is something like that. Like you have a bunch of data where your robot walked around and you have so much sensory data, and then you just want to use this data to train some policies. Like you don't have access to anything else. Like you cannot now have a robot that walks around and tries to do trial and error stuff. You already have this data. Then from this you want to learn something optimal. Like I mean, I'm not sure what are the edge case, what are the limitations and what you can maximally learn from such data sets, but I guess offline RL is a setting where you try to do this, because this is more common in the real world. Like you have robots that do stuff and you have sensory data, then you don't have access to a real robot that can wander around. And I mean, let's say you are a drone fleet, you have so much data coming in, how to use that or something.
Let me maybe give you an example of what I'm thinking about. So I took my garage and I painted a yellow line, and I have my rover walking on it.
Yeah.
And it's not doing a very good job, but in every frame, I have part of the yellow line, and the data shows how commands to the legs move the yellow line somehow.
Yeah.
Now I'm wondering if there's any automated method of me taking this data and saying your goal is for the yellow line to be in the middle. Okay, and since we're assuming some type of, let's call it linearity, in other words, if I have a picture and the line is here, so the same command that would move it one step would also, if it were in the middle, move it one step. And then using what you called offline reinforcement learning, it says, okay, now I know what to do. Let me try again, and it's going to keep to the yellow line. So is there, a bit like active learning, where you collect the information that you need in order to improve your learning as quickly as possible? Is there something like that that I can train my robot to collect information so that then I'll do offline learning and be learned?
So in offline reinforcement learning setting, you have this, you record your robot doing something, and then you want to learn what that something is. Like, I mean, you demonstrated to it how just the yellow line or something, and then you just want to extract following the yellow line policy from it. So let's say you demonstrated it 2 times maybe. So then there's something common in both the things, that yellow line is in the center. Then you can, but I'm not sure how you can alter the experience to learn a new task. Like probably the only thing common across 2 videos is following the yellow line. More than that, you cannot. Maybe follow a blue line, you can't do that.
Well, the task can be, let's say, it's a good question, but let me give you an example. Let's say the task is to be half of the time to the right of the line, and then 1 minute here and then 1 minute on the other side, 1 minute here, 1 minute on the other side. So that's a task that's atomic unit of be on the line, or be to the right of the line, or be to the left of the line, is in the data. The task itself requires learning. So I can imagine a task with atoms of the task are found in the data could be used for it. Because I've said it before, I don't like simulation that much. The world is very complex, and a small amount of simulation might make sense, but we should be able to learn by doing. So that's why I'm always looking for ways in which we can do something and learn something from what we did and do it better next time. By we, I mean the robot, of course.
Yeah. I'm not sure how you can define a specific goal after you collect the data. I'm not sure. Like
some of the research I've seen is it's called, what they do is like create the digital twin of the real world. So they sense the world and then create a digital twin and then do some learning and then reapply it back. So, but yeah, you need some good simulators for that. So that is one way to do it. There's some example of it on YouTube with NVIDIA's Isaac Sim. Post it in the Discord chat.
So if you had the sensor data, like you had I muted, no. So you have the video, and then you have the sensor data that says, here's what my motors were doing, the legs were doing, or whatever. And you train a model that was trying to predict based on the motor movements, what the video did. Like it was tracking the yellow line. And so you collected all the data, and then you run your neural net multiple times, whatever you got to do to train it on this data, so that it can decide like, oh, if I do this motor movement, I'll be able to predict with some degree of accuracy where that yellow line is going to go. That's your model. And then what you do in the second step is then like try to flip it backwards. Like if you're trying to say, I want to move this yellow line to the center, tell me what the motor movements are supposed to be. Is that way off base from how these things work?
So what you described, right, is the basic strategy used at least in adaptive control theory, which is slightly simpler than what Sai is talking about. But basically, you divide behavior into explore and exploit regimes. So explore is do random things to learn what you're capable of. So if I turn on this voltage, this motor moves this much. If I turn on that, it moves. So it's like basically thrashing around all your limbs to see what happens.
Right.
And that teaches you the model. But once you've learned the model, then you're able to define goals like, follow the yellow line, because now you have a causal and deterministic model of what you're capable of. And if you are given a goal like follow the yellow line, you can deterministically compute how to actually follow it because you have the model from the earlier thrashing around. So this approach is called dual control. I posted it in the Discord. And I think the difference between dual control approach and reinforcement learning is precisely the fact that you have these ambiguous goals that could be arbitrarily defined. And it's hard to learn a model rich enough that you can make all the possible goals deterministically solvable. Does that make sense? Like if you just have two motors and simple tasks like follow a line, you could probably learn a complete enough model of your capabilities that after that, if you're given a goal, you can just do it. But if you're given like a really complicated world, you cannot thrash around enough to actually extract all the dynamics of the world. So this,
yeah.
Does that make sense? Like,
Yeah.
I'll try. An example I can think of is if you have like a very simple world, but your robot is like maybe just 1 degree of freedom, like maybe it's like one joint, then it's a 1 degree of freedom learning problem where you thrash that one joint around and you learn a 1 degree model. But now if you say that you're in a world that has 100 rocks with different properties and they can roll and move in different ways, you have like a 1,000-dimensional model. And even though you only still have one actuator that you thrash around, the effects of that, depending on which rock you're next to, will be very different. So you can't, it would be intractable to try and learn how all the rocks move by just thrashing around. So that sort of sets a limit on this. So I think that the hard part of the problem in what Sai is describing is how do you actually simultaneously learn worthwhile goals and the rewards you get for following them and the capabilities that you have. The capabilities part is relatively easy. Learning the reward landscape can be arbitrarily hard, I think.
Yeah, I can put it in this way. Like if I'm a human, I want to get out of this house. I have some abstract goals. Like I just open the door back and I find another door and just get outside. I don't have to think about every limb movement that leads to the to me to escape the house when or something like that. But a reinforcement learning agent has this problem of exploration and exploitation, where exploration in this very thrashing the limb around space is not really effective. Like you can't explore the entire world by thinking of the world in terms of limb movements. You have to think of them in terms of higher and higher abstractions, and it's a problem called hierarchy. In reinforcement learning, this problem is phrased as hierarchical reinforcement learning. How do you learn abstract goals then your low level agent can solve or something like that? So yeah, and even in this cross embodiment setting, I guess this is another thing that is common across embodiments. Like you can talk of goals as common in some abstract level, and then the embodiments are like low level agents that try to solve that in their abstraction level. So yeah, but this hierarchical reinforcement learning is still thought of as a holy grail. Like there's no clear approach yet on how to do it with neural networks. Like yeah. And Meyer, in terms of what you are asking, I guess there was something similar in this research project where they wanted to look on how do you, you have this robots moving around the world and collecting so much sensory data, but most of it is going to be the same. Like it's going to see the same rock or something like that. But there are some informative moments in them. Like, for the first time, your robot is finding a staircase and falling down or something like that. Then how do you extract some data that is more useful? Like yeah, that was one line of research they were looking at, but I'm not sure it's related to active learning or collecting data and then using it, and what sorts of information theoretic metrics you can put on a lot of data sets to extract the most salient sets of data out, and then you can train something on it. So the idea is like you can't store all the data in the cloud or something, so you just have to extract something salient every time it occurs, and then you can probably do some training on it.
Yeah, but I disagree with that statement that I can't store all the data. Why not? Just put a bigger disk. Or unless I misunderstand what you mean.
Maybe not even store. I guess you just need the long tail of the data. You don't need the things that occur so commonly that maybe I guess you can put it in a different way. Like you just want more variance to the data. You don't. Maybe you can store everything for your spider bot. Let's say you had 100 spider bots or 1,000 drones going around in the real world. Probably storage might be a problem, and bandwidth and all that. Maybe forgetting of, let's say for now we can just store everything, but even then when you want to train, you want something salient to train on. So I guess in Tesla they had the similar problem, like whenever I don't think they can use every, I remember in one video where Karpathy was saying something like they can't, I mean, training again and again on the same data is just going to, I mean, similar data is not going to work. They need this exceptions and long tail events that they want to capture. And yeah, so
I think the
probably,
example he used was the wiper turning on randomly when the car was entering a tunnel. So having millions of data points of when the wiper is on or off in random weather conditions doesn't help, because the specific corner case is you're entering a tunnel and it comes on. I think that something like that was an example he used. So yeah, that's a good illustration. And I think what you pointed out is right. Like, you have to be able to pick up on salient events as they occur. You can't like just go around searching the whole state space. And another complexity that happens is often the whole state space is not safe to learn in. So one of the problems in dual control that kept coming up was when you're doing the thrashing around is basically inject a white noise signal into all your actuator channels. So if you have like a 3 degree of freedom thing, you would inject white noise into all 3. The problem is the plant may be unstable, and while trying to learn, you might actually walk off a cliff. So one of the reasons you want to be much more careful in exploration exploitation is you can actually learn the whole state space in a safe way. Like, you can learn how to move safely from point A to point B without falling off a cliff. And if there is a cliff in the environment, maybe you can go around the cliff, right? So that's one of the big challenges of that's a huge infinite negative reward in the environment.
yeah.
Right.
That's all among the things that they're looking at here. I mean, most of the RL stuff you see, it's about low level control, and the things we want to work at is a bit more high level. Let's say you had the Boston Dynamics dog. You don't care about controlling its. I mean, they have a good enough policy to control the low level actuators. You don't want to think in that level. Then what can you do in a higher level? Like for the negative reward case, one thing is street crossing. When you want to train a robot to cross a street, how do you have a notion of this risk? Like, I mean, some actions you can do, but you shouldn't do it when you are training, because it will just lead to infinite negative reward. Like, you can collide on something or something like that. Like, yeah.
Okay, thank you. Any other questions? Okay, so next week we have Vine presenting, right? You're on mute.
Right. Yep. Yeah. Model rocketry, if you guys are still interested.
We all are, especially if it goes boom.
So not sure how much it'll relate to rovers, but we'll see.
And the week after that, we're supposed to have a session where we talk about our plan for the year demo, end of year demo. So start thinking about it, please.
All right.